He's also a registered professional engineer. He held a PhD degree in construction engineering and management from Iowa State University with approximately 6 years of teaching experience and 6 years of professional working experience. At Iowa State, he taught project management and senior design. And at Central Washington University, he teaches the following courses: construction documents, plane surveying, building service systems, soils and foundations, senior design, and construction finance and business management. His research interests are disadvantaged business management, disadvantaged business enterprises, modular construction, and integrated project delivery methods. He advocates for sustainability and cost efficiency in both engineering and construction and promotes diversity and inclusion in both workforce development and business enterprises. And now let's welcome Dr. Dang to give us a lecture.
Thank you. Thank you very much for the warm introduction. Um, Let me share my screen and we'll get started. Can you see my shared screen, the PowerPoint?
Yeah, that
Yes.
works.
Great. Thank you for verify that. And my topic today is decoding CAM, BIM, VDC, DPD, DT framework. Will one fit all or all be in one? So it will be a relatively simple lecture. It is more of an introduction to all of you to the framework, different technologies that we're using in the construction industry, rather than an in-depth review of each one of them. So hopefully by the end of the lecture, you get to know them, and also it will spark some interest from you so that you will learn more in either one of them. So um, if you have any questions, feel free to type your questions in the chat window or Q&A session. I will address them at the end of the presentation. You also have my contact information here, my email. So if you have any questions after the presentation, you can email me and ask me as well. So a quick agenda or learning objective for today's presentation. I will introduce CAD, CAD, BIM, VDC, PDP, and DT technologies. Then we'll review and compare them through examples. A couple of learning objectives for you is to distinguish CAD, BIM, VDC, PDP, and DT, and discuss potential applications in best practices. So right now, when you see those, they're all abbreviations or acronyms, and we will go through each one of them. But before we do that, let's look into a little bit history on the use of technology in the construction industry. So long time ago, when people are building houses or buildings, there wasn't architects or engineer. The role wasn't there. It's simply one master builder who is in charge of everything. So this master builder has no plan or hand-drawn plan. Based on the hand-drawn plan or the knowledge and experience of this master builder, he or she will um, will build the building. Later on, as building became more complex and also infrastructure became more complex, we have separate roles. So we have architects, we have engineers, then we have contractors, and the relationship start becoming changed from the owner, the designer, the builder with different project delivery. And we also change from hand drawn plans to computer aided design, CAD. And then we start using building information modeling. Later on, as project become more complex and large, there's a requirement for collaboration. So we have virtual design in construction, digital project delivery, and digital twin application for integrated teams. The challenges that posed to all of us in the construction industry was that in architecture, engineering, and construction industry, AEC, is is that when we have the design, it's oftentimes difficult to change. There's also a lack of collaboration between different disciplines, and that potentially could result a lot of requests for information, change orders later on, and a lot of rework on the construction job site, and potentially there will be dispute claims against owners, against the engineer, and maybe against the contractor. So um, whenever things goes wrong, everyone start pointing fingers and everyone using their knowledge try to defend themselves. That's not a collaborative working environment. Using the technology, we'll be able to help us collaborate together. The first one I want to introduce is the computer-aided design. It's also called computer-aided drafting. It's a type of software that assists with the design process in all type of industries. In construction and also engineering, we use CAD to produce mainly construction documents, i.e. the drawings. So when I was in school, majored in civil engineering, I remember I took a course that's the engineering drafting course. At that time, AutoCAD or computer-aided design was relatively new. So we have to manually draw the plan on a large sheet of plan sheet. So we have to basically use all the drafting tools to draw them and also write the engineering characters. A probably gonna take one day or several days to produce one sheet of drawing, or even longer. And there was a joke that one of somebody's friends broke up with his girlfriend, and he just locked himself up in a building and produced 7 sheets of drawing. So it's very time consuming using hand drawn plans. So when we have computer-aided design using AutoCAD or CAD, we can produce drawing quickly, and we can also change them quickly. There's a trend here using CAD, and building information modeling became popular in roughly about 2000, starting roughly about 2000, and became popular in the last decades or so. And this picture kind of shows the CAD, the era of CAD, and the era of the building information modeling used here. So building information modeling is a process of generating and managing building data during its complete cycle from conceptual design through operation of the building. It is a process involving generating management digital representation of building objects, which are used during planning, design, construction, operation, maintenance of diverse physical infrastructures. It integrated workflow that enable architects, engineers, and builders to explore project digitally before it is built. So building information modeling is used to create the model, and there's a shift that when we create the build drawings, we used to start from 2D, and then we print it 2D drawing, we take it to the construction job site. There's a lot of review and revision to make sure information are accurate, and also the design is constructible. Because whenever there's a conflict, you need to go back and talk to the engineer and revise the design. So building information modeling allows us to see what the 3D is, and we start from the 3D object, we build the 3D model. Using the 3D model, we can take different views, the plan view, elevation view, section view, and then we provide more details how this view contains what information. There is an adoption curve for building information modeling. So when it first came, not all the people believe it's useful and beneficial, but it does come with associated costs, such as the license cost for the softwares and the training associated with how to use it and how to do it. So this curve kind of shows there is a decision-intensive software for which software do you use, whether you use AutoCAD, Revit, ArchiCAD, SketchUp, or some other software. And then there is a liability concerns. When we create a model, if the model is not accurate, who is liable for that model? So oftentimes when people using building information modeling, they use it to generate 2D drawings, and this is still the common practices right now, is that we use building information modeling to generate 2D drawings, and engineers still need to stamp on the 2D drawing to approve those drawings, and we are still using the 2D drawings for construction. We're using the 3D building information modeling for visualization most of the time. We don't use it for construction right now. And we will talk about more about BIM and how we could possibly to bring it to the level that we can use it for construction later. So there's also a learning curve, and there's investment in training, and then there's legacy software implementing changes in the BIM processes, and then there's construction knowledge integrated into building information modeling. When the disciplines are separated, we have architects, engineers, and contractors. Oftentimes the contractor's knowledge does not transfer back to the architects and engineers. So the architects and engineers may not know the material cost, which one is cheaper right now. And so they may select a design that's gonna cost more to build. And this stage here, the construction knowledge transfer from the contractor to the architects and engineer is very beneficial in the building information modeling. VDC is a virtual design and construction. It's a type of technology that creates digital model of buildings and project sets. Some company or individuals or professionals will take building information modeling the same as virtual design and construction. However, some other professionals may distinguish them. They will say the virtual design and construction is one level higher than the building information modeling because it integrates more features. And there's a different development, and we'll talk about that later in the lecture. So the architects, engineer, contractors use VDC model to visualize and plan building designs, processes, schedules, budget, and more. VDC technology allow company to analyze construction plan from start to finish before breaking ground. When you're looking at the description here, it does look very similar to the building information modeling, and but later on when we compare them, you will see a little bit nuances there. So I do have one example here. What I want to do is I want to copy this link and put it in the chat so that everyone may be able to access to it. Do I have the chat window? Okay, chat window. So if you're able to click on the link, go ahead and do that. So I'm going to pull up this link here. This is an example from Galeban Corporation. They have a virtual design and construction example here, where they have different rendering of their rooms. So you can see the exam. This is a hotel on a hospital project. So in a hospital project, you have exam rooms. If you click on one of those, it will take you there. You can also use your mouse to look around. You can drag it to the left or drag it to the right to look around of the room and see how things are laid out. And you can look on the floor as well. And this is a really good example of virtual design and construction, where everything is virtually built and you can explore it in the virtual model, or you can explore it using virtual reality or augmented reality devices. So there are a lot more rendering or virtual space here. This one is a waiting room. You can also look around here in the waiting room, and you can explore some other rooms from this link. Some other company also have their virtual design and construction team or their virtual design and construction philosophy. So what I'm going to show you is the examples from different companies. Let me see if I can.
I think nowadays.
So let me share my sound. All right. So this one is an example from a company called Katerra.
To build anything, you have to realize that construction is fundamentally changed. It's a manufacturing process. You know, parts and pieces are coming from all over the world. They're expected to come at a certain time. They're expected to fit within fractions of inches. And so there's really no other way to accomplish that level of coordination without using virtual design and construction.
It's a traditional process we've always done through shop drawings, but it's done much better and faster within a model because you're able to actually see every part and piece instead of digging through thousands of pages of documents.
It's indisputable the value that you get from incorporating VDC into a job. When you put it in the model and you can see everything in context, there's no room for interpretation. This is possible, we can build this.
Our main focus is how do we get a quality product? How do we reduce waste? How do we maintain schedule? And virtual design and construction is the answer to all three of those questions.
VDC actually stands for Virtual Design and Construction. The whole point of the process is to try to get the contractor involved in the design early on and get a constructible model created. I often use the analogy of a car on a conveyor belt. You don't see the guys trying to design a steering wheel as it's going down the conveyor belt. That's already been thought through, it's already in the model, they just bolt it on. That's our goal with VDC at Katerra. Getting engaged with the design team early so that they're not reworking their design to make it constructible is one of the most valuable things that we can offer when we're doing the VDC process.
This reduces the amount of CA that's needed during the project. By doing so, we get to a complete design much faster.
The whole concept of what we're really trying to do is break down the silos. The architect is usually modeling, structural engineer, landscape engineer. So our first thing that we do is to say, we need to establish out of many models, what is our source of truth?
We need to be in there well before construction starts. Then we can actually execute in the field with less problems and less challenges.
4D modeling is kind of the concept of taking time and relating that to a 3D model. So now that you have a representation of what you want, what's the order in which it's going to be constructed?
By using 4D, we're able to take time and associate it with the model, bring it together, and actually be able to visually see how the building is going to come together.
Here at Katerra, we're really pushing to create the 3D model as our instrument of service opposed to the 2D documents. It sounds like a small thing, but it's a huge dynamic change. It's being able to look at things unashamed. This is how this building is going to go together. We see every part and piece. That way we can have complete confidence in what we're producing. Having a GC's input and utilizing VDC to validate that input is really critical to saving money and driving down costs and schedule.
30% of construction costs right now is in rework. Using VDC helps us dramatically reduce that rework because we are planning the work and clashing the work early in the project before we ever are in the field. So VDC helps us immensely in the planning of the project. Typically, a schedule stands apart from the VDC process.
It's really cool to be able to take that model with the schedule and say, here's what was going to go in today. Here's what needs to happen next. Here's where people are going to be working. Showing that to subcontractors is very powerful. VDC has an important role in safety. There's been projects where you would look at a shoring scenario or condition where it would have been a dangerous thing to install. And so with the 4D modeling, we're able to say, we can't safely build that. And we were able to make changes in the planning stage before we went out there and executed the work.
Here in Katerra, we're uniquely situated where we have the design team, we have the engineering teams, we have the construction teams, we have the whole process chain. We can all work under one umbrella where we can have transparency in a really meaningful way.
In the past, VDC has been something that lives in the office. But as we move forward into the future, we're bringing the field along with us and we're training them. And now we're able to use BIM boxes in the field and we can see that live iteration of the model where they can interact with it and see real live updates and actually look at it in a 3D environment.
From the owner's perspective, if their focus is actually being motivated to get this thing built and get it open and get some clients in there, then VDC is the most effective route to get there.
One of the great things about Katerra and the reason I'm here at Katerra is they see the future. They see that VDC is the way to go.
So working at Katerra for me means innovation and challenge. You know, we're constantly looking for what's the best tool, what's the most efficient way to do our job. And the VDC process is really what allows us to be able to do that.
So in the video, you probably see a lot of things. You probably saw a woman wearing VR goggles. You saw how it improved collaboration, how it improved scheduling, estimating, safety, a lot of aspects. This is one company is taking initiative to improve their virtual design and construction practices. I have another example in the next slide from a different company called Hinson Fells.
Hinson Phelps is leading the way in innovation. We are constantly creating new efficiencies that translates into better value for our clients. Being at the forefront of construction technology has allowed us to work with many of the leading technology partners, putting us in a position to help define the technology landscape. We're also using technologies now that we're collecting them to surface this information. Like for mixed reality, we're using products like the Microsoft HoloLens, where we're able to do constructability, design validation, install validation, and even sometimes to help us do layout. I think now that we've got great technology to capture data, to manage the data, leveraging on machine learning and artificial intelligence, we're able to take that data and have it work for us instead of us working to create that data. But now we're getting data in real time, in dashboard format, allowing us to better manage the job, and ultimately for the owners as they're doing their budgeting and their cost analysis, again, getting to the information that's most important to them. Working at Hensel Phelps, you become part of shaping the construction industry, and that is very exciting to me.
So in this video, you probably saw there's a drone flying around on the job site doing surveying or job site management. There's other technology that they use and integrated in their project. They're collecting real-time data. They're using ladder scanning to get as-built conditions. So there's a lot of things you could possibly integrate into the virtual design and construction processes. So the digital project, moving on to the digital project delivery, DPD, this is relatively new. Digital project delivery is actually delivering projects using digital data contains in advanced models, whether 2D or 3D, and machine readable technical requirements. So in DPD, everything will become digital. The common practices right now is to use the hard copies. You bring the hard copy on the job site, you look at the hard copy, and you will mark on the hard copy as you are doing the construction. At the end of the construction, you have a red line copy because as a general contractor, you will mark on the drawing in red and mark the as-built condition if it is different compared to the design. And then you need to keep that document for probably at least 5 years or more to make sure there isn't any issues with the as-built condition. Or if there's any maintenance that's needed in the future, you can go back and reference to the as-built condition. However, in the digital project delivery approach, everything becomes digital. So you have files in PDF or other digital format to store in your computer. You can also possibly have a model, a 3D model that contains different digital data about the cost, about the different features of the equipment, the size, function, etc. that will help you to do your facility management, as well as operation and maintenance in DPD. So there's one example from Gamma Construction DPD. This one actually use IDPD. They call it Integrated Digital Project Delivery. There isn't much explanation in the video, so I will play the video, and as the video going on, I will kind of explain what they're talking about in the video. So you won't hear any sound from the video because I muted the audio here. Basically, they're just playing music background, and everything is explained in the video. So they are using a sixth dimension for IDPD, which is called integrated digital project delivery. So they say the 5 elements are 10D, BIM, VR, and AR. So building information modeling will have multiple dimensions. And I will talk about BIM as one example in the following lecture. And I will explain the multiple dimension, what does it mean. So they have a 10-dimension building information modeling with the integration of VR and AR. They have DF management in Mac. They have digital project management, digital handover, Industry 4.0 operation, and data-rich BIM. So building information modeling, BIM, is a part of the DPD. And DPD is one level higher or bigger than the building information modeling and virtual design and construction. So if we look at the breakdown, the data-rich building information modeling, that's what they're using. And there's a project example. This is a 3D scan coordinate points on the job site. And this one is the topographic on the job site, etc. So 95% serving cost in one Taiku place. Eliminate errors in this project. Global Switch Data Center. This is another project. They have their E&M model. They have high level of details in the model. And then move on to their 10-dimension building information modeling with AR and VR. This is a different project where they build a model and they have earlier client engagement. They have a common data environment, and then they have design collaboration through VR. And this is a visualized schedule using Synchro Pro. You can tell the dates change and then the activities going on. This is a different example in scanning the existing condition and then using the scanned data to build a virtual model. This one is the example of manufacturing and assembly for curtain walls. If your model is accurate, you can use the information contained in the model for particular parts. For the curtain walls, you can use those information for manufacturing. 75% offset construction, so your model can also integrate it with modular construction or prefabrication. You can build it in the shop and then ship it to the job site. This one goes back to the data center again. Their high precision assembly. Some of the data center or other infrastructure have a high level of accuracy requirement. So you have to be pretty accurate to build it, to make it work. And then they have a digital project management. So in this one, they put ground movement sensor to collect real-time data in the ground, and also real-time set control. This is probably because the soil is probably not good. They need to monitor the underground condition. This one goes back to the data center again, talk about concrete strength sensor to monitor the strength of the concrete and shorter cycle time. This one uses computer vision to identify the workers on the job site, automated worker count, dashboard reduction 20% project management time. The digital handover is another dimension here, which they talk about digital quality assurance, as-built verification. So you can measure the ladder, using the ladder scan, measure the as-built condition, compare with the model to see if they're accurate or not. Industry 4.0 operation might be relatively new to some of you. There is Industry 1.0 goes up to 3, 4. Industry 4.0 involves robotics and assistive technologies, such as the things you can wear to help you lift heavy equipment, or this Industry 4.0 is like your phone. You have 2G, 3G, 4G, 5G. Now we're talking about 5G and 6G, similar to the Industry 4.0, 5.0, or 6.0 in the future. So that's the concept of digital project delivery. The next one is called digital twins or digital twin. Digital twin is a virtual model of a building that collects real-world information about the structure through sensor, drone, and other wireless technology. The twin continues to learn from multiple sources, including advanced analytics, machine learning algorithms, and artificial intelligence to gain valuable insights about the performance, operation, or profitability of a project, whether built or in progress. So whether it's built or in progress, using digital twin can gain a lot of insight through the data, so that you can make data-informed decisions. Digital twin is, relatively speaking, it's on a large scale. It's bigger than a digital project delivery. And in a digital twin, you can model one element, one building, or you can model many elements, many building with the project site condition, with the transportation, etc. So digital twin is actually came from aerospace engineer from NASA, and this video explains digital twin in a very simple way, but in a very simple but detailed way. So I want to show this video to all of you, so that you get the concept of using digital twin in construction in the future.
So Dion gave me an assignment. He said, Chris, I want you to make digital twin simple, but detailed. So here we go. Digital twin, simple, but detailed. Okay? First, we're missing a clicker. Let's go ahead and roll a little video here. Digital twin is the ability to take a virtual representation of the elements and the dynamics of how an Internet of Things device operates and works. It's more than a blueprint. It's more than a schematic. It's not just a picture. It's a lot more than a pair of glasses. It's a virtual representation of both the elements and the dynamics of how an Internet of Things device operates and lives throughout its life cycle. It's an understanding of all of its dynamics, whether those are electrons that move or whether it's the device that's moving itself. It's about understanding the elements that compose it and the dynamics of how that device is put together. Done correctly, a digital twin will influence how design, build, and operations of a device are constructed in a single life cycle. The design phase is where engineering tooling comes together, bringing together physical elements, physical bill of materials, pulling together virtual elements. You heard about the software on the cars and all the different elements and the chips that are there. Being able to coordinate and collaborate those together into a single facility of operational-oriented design that is designed to bring out the highest quality product. In the build phase, it's about yield. It's about understanding how the devices that make the product influence the product's tolerances and stresses and designs. And it's about better manufacturing to drive the correct tolerances and correct outcomes that you want to see for the product that you're actually making. And then third, a digital twin facilitates the actual operation of the product as well. Products age. Products go through different environments. They deal with things like weather. And they have different tolerances, and they shift. They drift. And so your digital twin needs to drift along with those products as they age. And that feedback, when done correctly, not only facilitates the operations of the product, but helps facilitate better design and better manufacturing by the lessons that are learned and the recalibration that takes place along the way. So quite simply, a digital twin, virtual representation of the elements and the dynamics of an Internet of Things device. It affects both the design, the build, and the operations of how products pull together. There's some essential capabilities that must be present for you to be active in a digital twin. First, you have to apply analytics at every step. The amount of information that we're dealing with to apply digital twin to a small device or to a complex device such as an automobile or an aircraft is staggering. Analytics has to be both real-time, it has to be operational, it has to be quality, it has to be predictive-oriented in its nature. The data that comes from a digital twin needs to be open. You have to be able to access it from a variety of different sources. You have to be able to pull it together into a federated model. And you have to be able to bring it together so that you can get that interaction, that dynamics to play. It's not just a schematic you're making. It's not just a picture you're making. You're actually making a dynamic model that you're going to shift as you go through both the design, the build, and the operations phase of what you do with the life cycle of that product. And then last, you're going to apply industry context. You may actually use the same product differently in two different industries and have two different digital twins for that one product based on how the industry uses that product. Whether it's a pump that's used in oil and gas or whether it's a pump that's used in municipal or wellness and water, the outcome is based on the industry context of how that device is going to be used. And so a digital twin not only captures the engineering aspects, but it also captures the industry context, the dynamics of how that product is used at the same time. Let's talk a little bit about how we do this at IBM. At IBM, we start with the Watson IoT platform. It is where we bring the data in. We connect to a variety of different data sources, direct devices themselves. We connect to engineering capabilities. We bring data in through partners such as Aris. From the physical side, we bring logical data in from our own portfolio. And around the IoT platform, we start to build context of the relationships of the information both over time and relationship to each other. Collapse and collect the information. Second, we apply cognitive insights. We operate on the data to understand its variances and tolerances and how it's used. We apply techniques in machine-to-machine, natural language processing, video, acoustical analytics, and more to help understand the dynamics of the information that you're being presented. So when you have the information and you have cognition taking place on it, what you can then do, which is the third step, which is the most valuable step, is you can dynamically recalibrate your environment. So a digital twin, when operating correctly, not only represents a picture, It's not only something that you can see in glasses and explode, but it actually works to dynamically recalibrate your environment, affecting the design, the build, and the operations phases of everything you do around that particular device. Well, where can you go see one of these? It's really simple. The first place that you go see one is go visit our own Watson IoT Center. We've instrumented several of the floors. We collect information, and we apply our digital twin models across both how we can show you dynamic recalibration around comfort. We can show it around efficiency of how the workspace is laid out and the interactions of the different types of office capabilities that are there. And last, we can show you the economic impact or the environmental impact of how the representation takes place at the same time. So come to our IoT Center. You can see our digital twin model in action. You can get your own picture of how it works, and we can talk to you about how you can apply it to your own business at the same time.
All right. I didn't realize I was muted. That was the introduction for the digital twin. And you can see digital twin takes a lot more information, and it's more agile and more real-time data give you answers to different measurement. So decoding and comparing, if we put them on in a table, and we're looking at all those 5 technologies, on the very far left column, I have those 5 CAD, BIM, VDC, DPD, and DT. And when we're looking at key characteristics, the CAD, AutoCAD, oftentimes help us produce the 2D drawings. And that's pretty much what we use it to do. Instead of doing hand-drawn plans, we're using CAD to produce 2D drawings in computer. However, when we use building information modeling, we start creating 3D model instead of 2D model. And there is a level of development in building information modeling. There's also a life cycle cost analysis possible in the building information modeling for simulation and analysis purposes. There's also a lot of collaboration when we're using BIM model. In VDC, we start using multiple dimensions of building information modeling called ND model, and we're also doing simulations. In DPD, digital project delivery, all documents will be digital with no hard copies. So in DPD, digital project delivery, typically you won't have any hard copy drawings. Well, people are gonna ask how are you going to hold engineers and architects accountable for their design, right? So the common practice right now is still using the 2D drawing and the stamps. So this will be something that need to be researched in the future to answer the question how the models can be reliable and also holding architects and engineers accountable for the construction. And DT is using all virtual models, basically create a virtual identical components of the reality. And the integrations of different technology are different too. So for CAD, the most common integration is construction documents. And for BIM, it can integrate with virtual reality, augmented reality, mixed reality, visualization, clash detection, which is identifying whether your duct is conflict with your plumbing pipe or your structure column is running into the way of the duct. You could do energy modeling to analyze the energy cost of the building, and you can do asset management, and it can also integrate with data analytics. In VDC, it often integrates in with estimate, schedule, cost control, risk management, and constructability review. So CAD or BIM, they were oftentimes used by architects and engineers. When we move into virtual design and construction, there is a heavy focus on construction. So that's why the integration part has more elements from the construction discipline. Digital project delivery can possibly integrate it with automation, robotics, cloud, Internet of Things, city information modeling, and in the last three, you can see they all have above plus additional features. So this means in each of the line, it includes everything above it and plus additional features that it can integrate here. In digital twin, same here, you have above, and you could possibly integrate it with artificial intelligence, machine learning, deep learning, natural language processing, and eventually use your digital twin for smart city application. Now we look at all of those and we compare them. There's a wide variety of software you could possibly use. And as a starter, I would recommend you to start with either Revit. Revit is a product by Autodesk, or start with ArchiCAD. So those two software, use it as a starter. And then later on, if you are doing design authoring, there's a bunch of software around design authoring that you could use. There's data management software, there's collaboration software, there is environmental software, visualization, VR, parametric modeling, conceptual modeling, data capture, etc. So there's a variety of software you could possibly use in the future. Start with those two and then explore more. And when you guys gain more knowledge, and hopefully one day you will become the leaders in one of those technologies. So the following slides, I'm going to give you a little bit more details about building information modeling and explain the different dimensions and level of development, and also some of the examples for clash detection. So this slide shows the building information modeling, n-dimension modeling. The ND modeling start from 1D, which is research and planning, research on existing condition, regulation, weather or site investigation. That's the first dimension. And then the second dimension is the drawing, which we often call it 2D drawings, right? So the second dimension 2D is the production of 2D drawings, such as plans, elevation views, and project documents, such as your specifications, contract documents, etc. They all can be called 2D. The third one is the production of a 3D model, rendering, walkthroughs, coordination, and clash detection. So when you have a 3D, that means you have a 3D model oftentimes. When we are looking at 4D model integrated with time. So when you have a 4D model, usually it's used for model, you have a model federation, which means you combine your building information modeling from architecture, structure, mechanical, electrical, plumbing into one, and possibly your subcontractor's model into one model. That's your model federation. And then you have virtual construction planning, scheduling, sequencing, equipment delivery. Those are all related to the time. In the 5D, you're going to integrate with cost. So you have material takeoffs, quantity, extractions, detailed cost estimate, cost comparison, life cycle cost analysis. They're all cost related in the 5D. In the 6D, you're looking to building performance, system performance, energy simulation or modeling, and also sustainability criteria. If you're going to get a LEED certification, LEED stands for Leadership in Energy and Environmental Design, which is a popular sustainability rating system in United States. So you are going to integrate the documentation and information in the 6D for sustainability. In the 7th dimension, you will use your model for facility management and also life cycle management strategies as built BIM for operation and maintenance. When you have a 3D model with all the digital data in the model, that can help you to come up with management strategy for your facility, and also can help you schedule the regular maintenance and operation for the building. And the 8D is safety, security, and emergency plan. Safety, job site safety is one. It's a common one that's used in BIM and also VDC. Safety and security can also mean you have a gates that will prevent other people to enter into your property, and you have an emergency plan in the case of earthquake or hurricane or flood, heavy rain, etc. You could escape from the building quickly or get out of the building quickly with your emergency plan. There are other dimensions such as smart home features or other features that could possibly added on to multiple dimensions. Sometimes they call it ND modeling or XD. It's the same thing. The building information modeling level of development developed by AIA, American Institute of Architects. They have 5 levels from 100 to 500. So LOD stands for level of development. Basically, LOD 100 is your pre-design model. You have large block chunks. They're not detailed, but they are symbol of what you're going to design when you're planning for that. In the second level, which is LOD 200, you have schematic design, which you have the shape of the building, what it looks like, the skin of the building, etc. And then you have design development. You have more details, which is 300 level. And when you get to 400 level, there's something in the middle called level of development 350, which is construction documentation. So in this stage or this level of development require you to finish your design and produce a document that can be signed and sealed by architects and engineers. So this is LOD 350 that can be used for construction. And then during construction, your model will be continually used for construction purposes. And then your model will be revised for as-built condition and will be continually used by the owner. You can see there are different color here and say who is the major user of the model. So in the pre-design, it's mainly the architects. And then schematic design, it's the engineer, development design, engineer and construction manager. And then construction stage will be the construction, and the last one is the owner, who is using the model probably for facility management, operation, and maintenance. Some examples of level of development. The picture on the left is an example for mechanical, electrical, and plumbing details. The one on the right is a structure detail. So for level 200, you have some pipes here, and then 300, you have boxes for control valves, and then 350, you have the control valves, And 400, you have more details here, and you probably have the true size of the balls. And 500, you have additional electrical controls there to show as-built condition. So this is one example for MEP, mechanical, electrical, and plumbing. Another example for structure is that in the pre-design LOD, level of development 100, you have two boxes or rectangular squares or rectangular boxes to represent a column and a foundation. And then in the schematic design, your column became a wet flange steel column, and then your foundation is a spread footing. In 300 level, you have more details in design development. And then 400 level, you have anchor bolts there. And your anchor bolts is designed, you can see here, it's vertically going down. And then in 500 as-built condition, you revise your design condition to as-built condition. You're using a G-shaped anchor bolts for construction. So that's how your model evolves as your design and construction progress later on. The commonly used building information modeling features done by one in 2014. There is a survey talk about schedule is the most commonly used features in building information modeling, and then cost. ROI stands for rate of return. RFI is stand for request for information. Whenever general contractor have a question on the drawing or on the design, they will send an RFI, request for information. And then the architect and engineer will look at the RFIs and explain it and respond to RFI so that the contractors can move on in construction. Reworks, change order, those are contractors' activities. And defects, productivity, quality, those are also contractors' features. Energy is from owner's perspective, doing energy modeling, and waste control, safety, risk, quantity takeoff, and claims. So quantity is not commonly used unless your model is very well developed and include all the necessary components. So a good example of building information modeling or BIM model is that it can include part or material-based information as well as geospatial, financial, procurement, and logistical information. So when you have the conceptual model here, and then you have the actionable model that will tell you the connection details, the embeds, MEP, pipes, the reinforcement in the wall, and also the bolts, the formwork for the foundation, etc. You can build all of those details in the model. And this is an example for building information modeling, but the concept and the model can be used for others like virtual design construction, digital project delivery, or digital twin. Some of the collaboration examples here using BIM as a tool. In the design phase, the architects, cost engineer, client, authority department, etc., and contractor, they all can collaborate together using the same model. During the construction phase, the contractor can use the model to communicate with clients, subcontractors, consultants, building service engineers, and their suppliers, etc. So that's how they communicate. You can tell there's a key or initiator, which is the architects in the design phase, and then there's the contractor become the key or the initiator in the construction phase. Sometimes the engineer may also become the key or initiator, and some company may have a dedicated person who is building information modeling coordinator or BIM manager, and their role will be managing the BIM model and coordinate with other people and stakeholders in the project. The bottom shows the design phases, setting information, design concepts, modular design analysis, coordination to overall design, on-site coordination, construction planning and management, etc. So this is a typical one. Others could be a little bit different, but they should be very similar. In the design coordination, this one is a workflow for 3D model. For internal coordination, then you have federated model assembly, which you combine model from different discipline. You have clash detection to remove all the conflicts in design or clashes. And then you have sorting, grouping of clashes, and design coordination meetings for design coordination. In construction or before construction, the contractors may do a constructability review. So they will take basically the 2D drawings or the 3D model, and they will develop their construction model that will comply with the construction codes, specification, tolerance check, etc. And then they will have a building information modeling implementation plan. And then with the 3D model, they will do their constructability review with general contractors, subcontractors, and also architects and engineers together to review if there is anything that need to be changed. Any change that will be discussed and sent back to the architects and engineer for review and approval. So this is a constructability review. The example of federated model is shown here. So the federated model is the one model that combines the architecture model, the structure model, mechanical model, fire protection model, electrical model, and plumbing model. When you combine all of them together, you have one central model that have all the components. And when a structural engineer designing the columns, the deck, they are not necessarily know where the mechanical duct will be. And same with the mechanical engineer, when they're designing their duct, they are not necessarily gonna know where the sprinkler pipe's gonna go, where the electrical lines or conduit gonna go, or the plumbing pipe. So there's often a lot of clashes in the model, in the federated model, and there is a lot of coordination that needs to be done to remove those clashes so that the engineers can resolve that before it gets into the field. So the utilization process of VR, when we're looking at clash detection, you can also using VR virtual reality to do clash detection or look at the model virtually. When you have the design coordination, and then you have integrated building information modeling model, and then you integrate with VR content using Oculus DK2 or mobile device or any other VR devices. You could possibly see the model virtually as if you are standing in the space. And then you can look at the shape of the panels, and you can look at the design, etc., whether it needs to be changed or not. And This one is an example of a hard clash. So in clash detection, there are hard clash or soft clash. The example of the hard clash is a plumbing and fire protection line run through HVAC duct. So the blue one, the vertical one, is the HVAC duct. And then you have your, which is your mechanical duct. You have your plumbing and fire protection line clash into the duct. So if we don't resolve this kind of issue in using building information modeling and it gets into the field, it will be expensive to reroute it. So the solution will be cut the pipe and then use 90-degree elbow, go around the duct, and then another 90-degree elbow and go back. Stuff like that. It will be very, very expensive. Or you need to change the duct to go around the pipe. And oftentimes in the design, we will move one or the other so that we will resolve it before it gets into the field. This page is an example of a soft clash, which the duct is lower than the head of the door in a service corridor and tunnel where the client needs at least 9 feet clearance. This is a standard height of the doors in this area to move any equipment. So this duct is lower than 9 feet. And what happens here is that when you move an equipment into the door and you try to move it further down into the hallway, and this duct might prevent you from moving forward because the duct is lower than 9 feet. So this is called a soft clash. And this can be changed fairly easily in the design phase by either raise the duct or change the size of the duct. You can make it a rectangular duct instead of a square duct. This picture shows an example of workflow clashes, which when you have a temporary scaffolding blocking the main entrance of the building, which is the access point. When you have this, then you won't be able to access the building, or you won't be able to move equipment or materials through the scaffolding into the building. So this needs to be removed before further work needs to be done. More example of using virtual reality for design review. Again, using virtual reality, you can identify missing support. This one right here, you have a missing support for a pipe spool. You can look at that using virtual reality. And this one is the example of augmented reality for design review. You can see the model in the actual space, and then you can use your control to zoom it in and or zoom it out to make it bigger or small. Some of the model has the connection details, so when you zoom it in, you can look at the connection details and review whether it's constructible or not, or look at the detail to use that for construction purposes. Now, this page is a glance of building information modeling from 2000 to 2030. This graphic is created by Yonsei University in 2017. So it gives kind of a rough idea where we're heading when we're using building information modeling. So mainly as a marketing and visualization tools, because we use rendering. We create rendering pictures for marketing purposes. And then later on, we have earlier coordination using BIM. And then we have 2 tracks of BIMs here. One is a drawing-led BIM. The other one will be visualization coordination BIM. And then we have integrated in full BIM here, which you integrate all the data into the BIM with different technologies and different project team members, etc. So here you can see this graphic using BIM 0, BIM 1.0, and then BIM 2.0, 3.0, 4.0 is Lean BIM, using BIM based on Lean philosophy and integrations, and stress or emphasis on Lean modular offset construction and automation. Then we have BIM 5.0, which is AI BIM. We use big data, Internet of Things, GIS, and AI to enable smart cities, connected BIM, and informed decision making through the life cycle of a project. So now we come to our ultimate questions about this presentation, right? So will one fit all, or will all be in one? So will one fit all? The answer is yes, but not really. So there isn't quite a true rigid yes or no question for will one fit all, because different people may have different perceptions or buy-in. And CAD, computer-aided design, was the most popular used in AEC industries. However, building information modeling became more popular than CAD in the recent years. And this can be, you can tell that by the first or second slides. So if I go back to this slide here, you can tell CAD was almost reached to 100% user adopted it, and then BIM is slowly growing in the last couple of decades. So whether one fit all or not, building information modeling and CAD pretty much can fit into any project. So those two can pretty much fit into any project, but it depends on the project team or the owner whether they want to use it and how they want to use it. Particularly for BIM, there is different level of development, and how much you use it, it will be very different when you're looking at different projects. Will all be in one? Yes, we're getting there, but not quite there yet. When you look at ND modeling for building information modeling, we're trying to put as much possible data as we can into one model and use that one model for the whole life cycle of the project, from the planning to the design, schematic design, design development, to construction document, to construction, to facility management, operation and maintenance, and then later on demolition and started over. So yes, will all be in one. It's possible all can be in one, but we still need more development in technology in the future to achieve that. So building information modeling still need to be adopted by other company. Not all the company are using BIM, particularly some of the smaller contractors, because there is a learning curve and also investment in softwares and people to enable or use building information modeling. So it requires project team buy-in and collaboration. Also need to identify the value added to the project team, especially the owner, so that the owner may have the budget for the building information modeling. If the owner doesn't have the budget, or the owner doesn't want to use BIM, then it's very unlikely you're going to use it. The expertise, software, training, and resources are also factors that affect how you use BIM. VDC is relatively new and it's gaining attention. DPD is being exported by a few. Some are using digital project delivery, and this will be the next step of the BIM and VDC. And digital twin offers the most value, and it is promising in the future. And there will be more research that need to be done in both VDC, DPD, and digital twin. I do have additional resources here. So if you click on this, well, I can put those in the chat window. If you want to click on the link and look into it, you can. The first one is CBIM from China. So this one has a lot of good project example here. The other two are from Autodesk. And that's the end of my presentation. So if you have any questions, type it in the Q&A session. I will address them one by one. So the first question I saw from Sanjeev, the question was how VDC is useful for Nepal. That's a great question. Most of the VDC, whether VDC is useful or not, the data is for projects, and those data are very much applicable, and it can be generalized into Nepal. So if you look at the benefit of VDC from different company, VDC technology can be used in Nepal for different projects. You may need to look into a few case studies to see what are the benefits, how much time does it save, how much cost does it save, etc. So additional case study in Nepal can be useful to answer your question. All right, any other questions about the framework or different technologies? Okay, I have another question from Asang. How often digital twin has to be assimilated with real world, or it is generated through real-time data? And what is the most sophisticated data for construction digital twin? Is it latter? That's a lot of questions, but to put it simple, yes, digital twin has to be assimilated with real world in the real time, pretty much. However, digital twin was originally developed from aerospace engineering. When the engineer want to launch a rocket and send a satellite into the sky, so they want to create a digital twin, which is a physical model. It's not a digital model, it's a physical model. And then they apply different simulation impacts on the physical model, which is a digital twin on Earth compared to the other model in the sky. So that's how it was developed, based on two identical physical models. The concept later emerged into digital model, digital twin, and the data need to be simulated real time. It is very common and also intensive for some industry like like automobile industry, the car industry, or some other manufacturing industry, maybe. For construction industry, during the construction phase, the data need to be updated real time. However, during facility management or the operation and maintenance, there isn't a lot of data feeds because the building is sitting there, you're simply using it. The data feeds or the data you collected is mainly the temperature, the indoor air quality, stuff like that. So there isn't a lot of activities going on. So relatively speaking, digital twin will be easier to maintain for facility management in the AEC industry. So it needs to be updated real time. And the sophisticated data for construction of digital twin, the level of sophistication of data is really depends on what data we're looking at. So LiDAR is basically different points, right? So it scans points and then stores into the computer. When we're looking at elements, you could have less sophisticated data. You could have simple data that represents good objects or building, or you can have a lot of data which will represent the same thing. So this will be a relative term, whether you have a lot of data or few data. Same with the image, you could have 1,000 image for the same or similar truck, or you can have one image for the same or similar truck. But those data can be identified, categorized by machine learning so that you can reduce the data to the manageable size. All right. I have another question here from Sunday. Thanks for the presentation, sir. Please kindly extend your explanation on the project monitoring part using DPD on how to detect and hold contractor accountable when they deviate from design, especially in a complex design. So DPD is relatively new. The concept of DPD is using digital files without hard copies. And because right now what we rely on is pretty much the hard copies. And even we're using PDF very often, we're using digital signature, but the industry still carry the hard copy in the field. And using mobile device is relatively new. So holding them accountable, holding contractor accountable right now, it's by contract. They have to follow your construction documents. If you're using a model delivery, which means you don't have construction documents, you give them a 3D model, and they need to follow your model. And this typically, the accountability part is typically written in the contract. So in the construction contract, part A, part B, part C, you need to do A, B, C. And I would say in DPD, you will need to use LiDAR scan or some other technology to verify the as-built condition aligns with your design. If it doesn't align, then you need to raise the question to the owner, to the contractor, why it doesn't align, what's going on. So you need to discuss about it. whether their deviation is acceptable or not. If their deviation is not acceptable, then it's the contractor's responsibility to demolish what they built already there and rebuild it to align with the model. All right, I have another question from Alim. Can we easily adopt VDC and BIM? Yes. You can easily adopt BIM. VDC might take a little bit more effort and resources. So building information modeling can be adopted in a few days or a few weeks. There are examples from different projects that the 90% or more of the project team does not have any building information modeling experiences. However, they have 3-hour training at the beginning of the project, and they were able to use building information modeling throughout the project. Of course, there's 3-hour training at the beginning of the project. There's a learning curve, and there's a continual training and development throughout the project. So it's pretty easy to adopt building information modeling. Virtual design and construction may require a little bit more resources, because building information modeling was originally emerged in the architecture and engineering industry. It wasn't oriented towards the construction needs. So you may need additional training or resources to incorporate estimating, scheduling, and construction planning, site logistic, sequencing into your model to use virtual design and construction. All right, any other questions?
All right, are there any questions? Okay, Dr. Dong, thank you so much for giving a well-prepared and wonderful lecture. And yeah, thank you so much.
Thank you. It's my pleasure to be here, and it's my pleasure to talk to all the students who are listening to me. Thank you for attending. I appreciate the opportunity, and let me know if you have any questions. I will type my email here in the chat window. So thanks again, and you all have a great day.
Okay, thank you, Dr. Dong. Thank you so much again.
Yep.
And everyone, that's all for today. The first lecture tomorrow will be at 3 p.m. Beijing time, and we'll see you all then. Thank you. Thank you. Bye.
Bye.
Thank you.